Good afternoon. In the following presentation, we are going to talk about one of the fields of quantum technologies emerging today, which is quantum communications. The work that we have presented is entitled as Madrid Quantum Network, a first step to quantum internet. We are going to see a brief introduction on the fundamentals of quantum communications and its ultimate goal, which is the quantum internet. We are going to comment on the quantum communications networks that have been most relevant over the years, and we are going to focus on the Madrid Quantum Network. Finally, we are going to see a series of projects that are currently running in Europe. Let's start. As many of you have already heard, the arrival of quantum computers is getting closer and closer, which will bring great advances for science and engineering, such as the development of artificial intelligence algorithms or the design of new materials, all thanks to the great computing capacity that they will have. But this large computing power also means that the cryptographic algorithms used today, such as RSA, elliptic curve, Diffie-Hellman, can be broken with a quantum computer. Therefore, a new era begins in which new cyber threats led by quantum computer will appear. Therefore, new encryption methods resistant to this attack are necessary. Two types of solutions are currently being worked on. Post-quantum cryptography, which develop new classical encryption algorithms that are resistant to attack by a quantum computer, short resistant, and quantum cryptography, where protocols such as QKD, quantum key distribution, are capable of distributing a secret symmetric key between two users making use of the laws of quantum mechanics. It is also resistant to quantum computers and to any type of computer since they don't depend on the computational complexity of a mathematical problem. It should be noted that all this new scenario is going to have a large impact both in civil environments such as critical infrastructures and in the military environment. Specifically, in the case of the current hybrid wars, the robustness against these new threats is going to be critical. One way to ensure the security in cyberspace is by using quantum communication to distribute symmetric keys. Quantum communications are based on the sending and receiving of qubits. There are different physical qubit embodiments, but in the case of quantum communication, one of the most used is photons with a certain polarization. These photons can be in state 0, for example, when they are horizontally polarized, in state 1, when they are vertically polarized, or in a superposition of state 0 and 1. This means that when measuring it, we have a certain probability that the result is 0 and a certain probability that it is 1. The advantage of this qubit is that unlike classical bits, this cannot be perfectly copied because this process will alter the information content. This property is known as non-cloning theorem. This is a great property since it allows detecting intruders in the quantum communication channel, although it cannot be distinguished from noise. Another property that these qubits have is that a pair of entangled qubits can be generated. These qubits are correlated with each other. In that case, even though those qubits are separated from each other a large distance, when measuring one of them, the state of the other is instantly determined. But of course, this cannot be used to transmit signals faster than the speed of light. The ultimate goal of quantum communications is to achieve the quantum internet. First of all, the quantum internet is not going to be a replacement for the classic internet, but the objective is that they are complementary and that the former provides security in communications and new functionalities. Quantum internet can be defined as the communication between various remote nodes through quantum channels guarded by quantum cryptographic protocols. Among the properties of the quantum internet that are described in the available bibliography, it is indicated that the quantum internet has to communicate quantum information between nodes, cover long distances through quantum repeaters, trusted nodes, or satellites, as we'll see later, generate and distribute entangled pairs between nodes, and classical and quantum communications should be hosted in the same infrastructure. On the other hand, the components that make up the architecture of the quantum internet are the quantum channels through which the qubits are transmitted. They can be fiber optic channels, open air, or through space. Quantum repeaters, which are necessary to reach unlimited distances. Thousands of kilometers can be covered using satellites, but in optical fiber networks, distances are limited to a few hundred kilometers. They pose a great challenge since, as we have seen before, qubits cannot be replicated due to the no-cloning property. Quantum memories, which are used to store qubits in case we want to process them later or perform operations on them. And the end nodes, which are the nodes between which the communication takes place. The phases to achieve the quantum internet of the future can be considered as increases in functionalities that led to an increase in the difficulty of developments. In a first phase, we would have communication networks based on trusted repeaters. That is, by chaining quantum key distribution processes between pairs of nodes, guaranteeing that the intermediate nodes are reliable. In phase 2, with networks based on protocols called prepare and measure, phase 3, it will be possible to generate and send entangled pairs. In phase 4, quantum memories are already introduced. In phase 5, an increase in the storage capacity of the qubits is expected, and in the final phase, phase 6, the computing power of the quantum computers is integrated. Now we're going to see a more relaxed definition of the quantum internet that allows us to consider some of the currently existing networks within this framework. First of all, we can consider that we have quantum internet since stage 1, but it is a quantum internet with fewer functionalities than the quantum internet of stage 6. We consider that basic requirements to start talking about quantum internet are those indicated on the slide. The nodes of the network shall be capable of transmitting quantum information to each other. Each node shall have quantum key distribution system capable of generating symmetric key between two nodes of the network. It is necessary an application layer with different functionalities that use the keys generated by QKD, and it is convenient to be a hybrid system that integrates quantum channels in classical communication infrastructures, working both simultaneously. The advantage of this quantum internet with fewer functionalities is that it is already feasible with the technologies that is available today and provides secure communication against quantum computers. In addition, another advantage is that it can be deployed as a fully operational intranet system, which are infrastructures widely used in NATO facilities. The advantages that quantum internet will bring are high long-term and unconditional information theoretic security. In other words, security doesn't depend on computational assumption. This is thanks to the fact that quantum key distribution protocols allow creating symmetric keys whose security is rooted in the laws of physics. Quantum cryptographic protocols beyond QKD, such as quantum digital signature, oblivious transfer, quantum secret sharing, etc. This will allow to increase the level of security, allowing, for example, the authentication of users or the sharing of partial information. An increase in the efficiency of quantum cryptographic protocols is expected compared to the classic ones, under the same operating condition. This is not included in the relaxed definition, which doesn't include entanglement, but there will be a new way of transmitting information through quantum teleportation. Broadly speaking, we want to transmit information from user A to user B, shown in the image. To do this, an entangled pair is created between user A and user B. Then a series of operations are carried out between the qubit that contains the information that A wants to transmit, which is the gray circle in the image, and the qubit of A that is part of the entangled pair. Finally, B performs a series of operations that allow him to extract the information from the gray qubit without A having physically sent it to him. Now we are going to comment on the quantum communication networks that have been most relevant throughout the years. Here we have a summary of the most relevant and well-known quantum networks. We have the quantum network in Madrid, which is the focus of this work, the DARPA project in the United States, the SECO-QC network in Vienna, the Tokyo network, UQCC, and all the networks that have been developed in China. Most of them are optical fiber networks. Some of them, like DARPA and SECO-QC, have segments in which photons travel through the air. The last two references correspond to the transmission of entangled photon pairs via satellite, also achieved by Chinese research groups. All these terrestrial networks are based on trusted repeaters and therefore are on stage 1 of the quantum internet. They also fall within the relaxed definition of quantum internet since they meet the minimum requirement. About the Madrid Quantum Network, it consists of 12 nodes distributed between research centers, universities, and companies. The type of qubit that is transmitted in the network are photons, and the quantum channels are fiber optic. These quantum channels coexist with the classic channels in the same telecommunications infrastructure. It is also a software-defined network that allows integrating devices from any vendor, optimizing the network, and deploying services more quickly. This gives the network great flexibility and dynamism. The Madrid Quantum Network has implemented a series of standards from the DFC, which is a standardization body. This will favor the future integration of the Madrid Quantum Network with other fiber optic networks or with other quantum nodes via satellite. With all the above, we have that the Madrid Quantum Network is a secure, hybrid, flexible, programmable, scalable, versatile, and heterogeneous network, and could be considered quantum internet with the relaxed definition. Finally, we are going to quickly see some of the initiatives and projects that are being carried out in Europe. In 2018, the Quantum Flagship began, which is an initiative founded by the European Union for the research of quantum technologies on a large scale. This includes quantum communications, quantum sensors, quantum computing, etc. In quantum communications, 3 projects were founded: CIVIC, QAIA, and QRange, showing the interest of the European Union in quantum communications. Moreover, for quantum communications, the European Commission has created the OpenQKD initiative, which is not a project of the Quantum Flagship, but is recognized as the first stage of the EuroQCI, which we will talk about later. OpenQKD aims to put Europe at the forefront of the quantum communications capabilities. This initiative aims to integrate secure quantum solutions from the entire European digital landscape and create testbeds, demonstrators, and use cases to increase the functionalities of the European network. The Madrid Quantum Network is one of the nodes of this project. The EuroQCI is an European initiative launched in 2021 that will end in 2027. It is an agreement to work together with the European Commission and the European Space Agency for the development of a pan-European quantum communication infrastructure. This infrastructure will consist on a ground segment made up of the existing fiber networks in the main cities and a space segment for the long-distance communications to connect different countries. It is intended to increase the security of European encryption systems and critical infrastructures against cyber threats, store and exchange sensitive information safely, and preserve government data. On the other hand, the General Direction of Armament and Materials of Spain has published a document with a technological and innovation strategy in defense in which quantum technologies are beginning to be taken into account. An initiative called Callaway Mission is also being carried out, in which a consortium composed mostly of Spanish companies is proposing the inclusion of a QKD mission as a hosted payload in future SpaceQR GEO satellite. The expected launch date of the satellite is in 2025. Thank you very much for your attention.